Welcome to Next Gen Manufacturing. Today, we're getting right into the heart of how we shape the modern world. We're talking about the theory of machining.
So how do we actually do that? How do we take a solid chunk of metal and sculpt it into something incredibly complex, with precision that's almost hard to believe? Well, the answer isn't about adding material. No, it's all about the controlled, powerful, and precise art of taking it away.
Okay, so here's our game plan. We're going to break this all down into 5 key parts. We'll start with the basic idea of removing material, get right into the anatomy of a perfect cut, look at the invisible forces at play, cover the 3 main ways we do this, and finally, see why all of this is still the foundation for next-gen manufacturing.
All right, let's dive right in. What is machining? Really, what's the core idea here?
So at its absolute heart, machining is a subtractive process. Unlike casting, where you're pouring metal, or 3D printing, where you're adding it layer by layer. Here, we're doing the exact opposite. We achieve that final, super precise shape by carving away everything that isn't the part. And it all happens through this incredible physical action called shear deformation, which creates a chip.
So why is this so important? Why is it literally a cornerstone of all modern technology? Well, look at this. You can use it with a ton of different materials. You can create pretty much any shape you can dream up. And the precision? It's just mind-blowing. We're talking tolerances tighter than a human hair. That's why it's in everything, from the engine in your car to the tiny components inside your phone.
Okay, now for the really cool part. We're going to zoom way in, right down to the microscopic level to see how we actually slice that material away. This is where the magic and the physics really happens.
So, you can imagine a real-world cut is super complex, right? It's all happening in 3 dimensions. To make sense of it, engineers came up with a simplified model. They call it the orthogonal cut. It basically strips away all that complexity so we can focus on one single straight cut. It lets us see the fundamental action.
And this is the moment of truth. As that tool pushes forward, it forces the material to basically give up along this one specific line. That's the shear plane. All the energy, all the action is happening right there, shearing the material away from the part and creating what we call a chip. It's amazing how much you can learn from something so simple. We're talking about the chip thickness ratio. All it is a comparison of the material's thickness before the cut to the thickness of that chip after it's been cut. And because the chip always gets thicker as it's formed, that ratio is always less than 1. It's a super simple number, but it tells engineers a whole lot about how efficient the cut is and what kind of forces are at play.
So, this battle between the tool and the workpiece, it doesn't always have the same outcome. Nope. Depending on the material you're cutting and how fast you're cutting it, you can get 4 totally different kinds of chips.
So first up, if you're working with something brittle, like cast iron, the chip doesn't form a nice, neat ribbon. Instead, it cracks and breaks into these little segments. That's a discontinuous chip. And you can probably guess this usually means a rougher surface finish. Definitely not what you want on a precision part.
On the other hand, if you're cutting a more flexible or ductile material, think aluminum, and you're doing it at high speed, you get this, a beautiful, long, flowing ribbon of metal. This is the continuous chip. It's often what machinists are aiming for, because it usually means you're getting a fantastic, smooth surface finish.
Now, sometimes things get a little messy. Under certain conditions, tiny bits of the material can actually weld themselves right onto the tip of the cutting tool. This is called a built-up edge, or BUE, and it's bad news. It's unstable, it grows, then breaks off, and it just wreaks havoc on your surface finish.
And then there's this one. When you're machining the really tough stuff, we're talking titanium, superalloys, the kind of materials used in jet engines and medical implants, you get these very distinct sawtooth chips. They're called serrated chips. Learning to manage this is absolutely key to making those high-tech, next-gen parts.
Okay, so we've seen the chip, but what about the stuff you can't see? I'm talking about the invisible world of immense forces and just an incredible amount of heat.
So, to really get a grip on what's happening, engineers are constantly measuring 2 main forces. First, you've got the cutting force. Think of this as the main muscle. It's the force pushing in the direction of the cut, and it's what determines how much power you need. Then you have the thrust force, which is trying to shove the tool away from the part. You have to control both.
And get this. This number is it's wild. Where does all that energy and power go? Almost all of it, a whopping 98%, is converted directly into heat. It's not going into breaking the material, it's just becoming pure heat.
And we are talking about serious heat. Right at that tiny point where the tool is shearing off the chip, temperatures can skyrocket to over 600 degrees Celsius. That's over 1100 degrees Fahrenheit. So you can see why managing this heat is one of the biggest challenges. It affects everything: how long your tools last, the final accuracy of the part, everything.
Okay, so we've got the theory down. Chips, forces, heat. Now let's bring it out of the lab and onto the workshop floor. How does this apply to the most common machining operations you'll see every day?
All right, meet the big three: turning, drilling, and milling. They're the workhorses of the industry. In turning, your part is spinning and a tool moves along it to create cylinders. Think of a baseball bat. In drilling, a spinning tool plunges into a stationary part to make a round hole, and with milling, a spinning cutter moves across the workpiece to create flat surfaces. The motions are different, but the fundamental physics of how that chip gets made, exactly the same.
Okay, let's bring it all home. How do these fundamental, century-old principles connect to the future, to next-gen manufacturing? And this, right here, is the key takeaway. It doesn't matter if you're looking at an old manual lathe or a brand new AI-driven CNC machine. The fundamental physics of how that one single chip is formed, it hasn't changed. It's the same. And understanding that basic physical interaction is still absolutely non-negotiable, no matter how smart our machines get.
I mean, this quote really puts it into perspective, doesn't it? The entire Industrial Revolution, the growth of modern economies, so much of it can be traced right back to these very operations. These principles didn't just build parts, they literally built the modern world. And they're still the foundation we're building the future on.
So that leaves us with one final big question to think about. As our factories get smarter, as automation and AI take over, will we ever engineer our way around this? Will the fundamental physics of making a single, humble chip ever become obsolete? Or is it here to stay, forever at the heart of how we make things?